This is a summary of lecture 2a and 2b. So what do you know? You know that when you get a function, you can do a total derivative. So for example, h is a function of t and p, no problem. You can write partial dh by dt, keeping p constant, partial dh by dp, keeping t constant. That's fine. And then you know what the difference between a differential is and a derivative. And there's also different notations for you to get familiar with, and you just work with it that suits your comfortability. But here this is partial dh by dt, where h is a function of t, where p is kept constant. Because it's exact, we're dealing with exact functions, you could also write it dh by dt, keeping p constant, and where h is a function of t. So when you look at the superscript, you just need to be comfortable with saying, oh, okay, so p is not in the denominator, therefore it is the constant. You could also have p brackets p at the subscript, or tp in the superscript. You also know how to obtain a partial either by introducing a variable or keeping a variable in that system constant. So for example, when you have dh by dt, you can have dh by dt, say p is constant, is also equal to be dh by dt, where p is constant. You also have learned or revised what exact equations are, and it's after writing your total derivative, the partial derivative of that partial should be equal to the partial derivative of that partial with respect to that variable. And because it's symmetry, you can be d by dt or dt by dp. You can swap them around, and this helps you later on when forming identities. You also learn differences and integrals, so where you have delta h12 is equal to dh of the integral is equal to h2 minus h1. And for path independent, we learned that it doesn't matter how you get there, your delta u or your delta h will be the same. Will always have the same value. But then we learned a bit in the last lecture 2b that there are actually path dependent variables, and those path dependent variables are, for example, in your USV space, you can have w is equal to the negative integral of p dv. That is when s entropy is constant, or q is equal to the integral of t ds, and that is when volume is constant. And because where this comes from is basically from canonical variables, when we learned the canonical variables, and we could write initially with our base function where u is a function of sv, we could also write du is equal to the partial du by ds plus the partial du by dv. And let me just move this down. What you learn from canonical variables is that from the source function we just said, fine, if we accept that u is a function of sv, we can write the total differential, but then at the same time let us use the thermodynamic definition of t, where tsv equals partial du by ds, and also psv is also equal to negative partial du by dv. So let us introduce two variables t and p And these are the thermodynamic, actually these are the thermodynamic definitions for T and P. And you go, okay, fine. So knowing this, what can we do? You can substitute it into this equation over here. And then we learned what canonical variables are. Actually, canonical variables is a terminology to describe for each function what the variables are for that function. So u, total derivative of u by s and v, is to define that s and v is its canonical variables, it's its base variables. You may find other functions where u is a function of t and p, or u is a function of p and v, but from the base canonical, without degrading it, its complete form, the canonical variables of u are s and v. Because why? From usv, in that usv space, oh, well, if I have, in that usv space, you can actually get quite valuable information, and we've seen that with the q and the w. So canonical variables it denotes the complete form of that function, and it helps us to find even more information about a thermodynamic system. So from our source function, from the canonical variable source functions, by using the other thermodynamic definitions, where a is equal to u minus ts, and where h is equal to u plus pv, and where g is equal to u minus ts plus pv, then what? Then you can also get canonical variables for these equations. For a, so we were able to derive that dA equals negative p dv minus s dt, where a's canonical variables are vt, and that's its base. Those are its canonical variables in its simplest form. You can start to write a in terms of other variables, but the avt space is the purest space, its original space, and from then you can find other functions. Then for the h, we found that dh was equal to tds plus vdp, and then therefore h's canonical variables are s and p, and in the sp space you can find joules as well, but s and p are the canonical variables that help define the H system. And then also you have dg is equal to negative sdt plus vdp, and the canonical variables of g is t and p. And inherently you could find more identities. You could find more identities for p and s and t and v and s and v with respect to g, h and a. And even though we were showing you the maths, inherently, like later on in the later lectures, I'll show you, oh, what A is, what U is, what G is. But we note H kind of represents enthalpy, G kind of represents Gibbs, U is internal energy, T and P are temperature and pressure, V is volume, and A is Helmholtz. So these represent thermodynamic properties, but we use maths to just help further develop their understanding of it, and that we don't use the standard equations all the time. Sometimes we also use the differentials so that we could find the differences or integrals in the system. And then from then, what did we do? From then we learned Legendre transforms, so that's the Legendre transforms. So over here, these were the Legendre transforms by using our source function u as a function of SV. And then further from that is you can obtain Maxwell relations. And from obtaining Maxwell relations, you can obtain even more identities. And why would you want to do that? By finding more identities, then you can actually substitute in for another variable in case you don't have that certain variable in that system. So what are Maxwell relationships? Well, because you know the exactness, the exact definition, you use that to help you along your path as well. So for example, we take the definition of t was du by ds, and what can you do? Well, you just differentiate each side. You can differentiate it with respect to v, you can differentiate with respect to t or p, but for now, for example, I'm just differentiating both sides with respect to v. I'm not changing it because I'm doing it to both sides of the equation, and t is a function of sv, right? So then what can you get? You can get dt by dv is equal to d by ds du by dv, and earlier on we've defined negative p to equal du by dv. Okay, and this is a function of s, which implies that you can also get dt by dv is equal to negative d by ds p. Okay, so what do we have here? We have p, if you wanted your variables, t was a function of s and v, and p here is also a function of s and v, so p here is also a function of s and v. So in essence, they're still keeping the same independent variables, the canonical variables, but sometimes you can use Maxwell relations where you differentiate both sides and you use the concept of exactness to swap it around. Because why? You want to get new identities, because new identities can help you manipulating your functions just in case you don't have a dt by dv, or just in case you don't have a dp by ds. You could find, oh, but I do have a change in temperature with respect to volume, keeping entropy constant. Then in your thermodynamic equations you have identities to substitute in for it to find unknowns. And then what else did you learn? Yeah, so then after that you can derive even more different relations and identities. And then we went to the path independent variables, as I mentioned, path dependent variables, where you get w, we showed where w equals negative pdv and q equals tds. And from that you can draw that, okay, delta u equals w plus q. So on the work path where you found w, s entropy was constant, okay, entropy was constant, but then also q was 0, because then in this u path, your delta u12, your q term was 0. And then when your q equals tds, that was your delta u23, and there v was constant, but inherently also your w was 0. Okay, so w work was 0 on this tds path, and q was 0 on your pdv path, okay, on this work path. So that's another insight if you didn't see that. But what you want to take away from that is delta u is this state function, doesn't matter how you get there, but w and q can change. They can be different values to get you to your delta u, but your delta u will always be the same. And then chemical potential was another thing that was introduced, whereby your mu I is equal to partial derivative of u with respect to number of moles I, S, and with function of SVN, summation, well, square brackets, a matrix of in molecules. So what you want to take away from here is that this chemical potential only exists if you have multi-component systems. So far your equations that you see in your equation sheets are only for well, when we did them in the lecture, it's for pure components, because you can't have du by dni for one component. So therefore this is only for multi-component mixtures, which we'll learn in second semester, but it was to introduce you to it for in case when you have, say, for example, u is a function of SV and Nj molecules. And then in your formula you have du is equal to du by ds, where where oh, S is equal to where N and V, where N and V are kept constant, ds, plus du by dv ds, where sorry, that's dv, where S and N are kept constant, plus your summation of du by dnj where what? Where you have vs and ni components are kept constant, but ni must not equal nj, because then what's the point of having your partial derivative and differential over there? So this is to show you that if you have a mixture, your equation here where we showed earlier, your du can also equal to tds minus pdv plus the summation of mu dnj. And this mu here is basically for multi-component mixtures, and if you use I, you use I, if you use J, you use J. It's just to say that you have J components or you have I components if you want to take it to I, or you want to take it to J, or N components, but when it gets to that value, when you cannot partially differentiate itself and keeping itself constant. Okay, so you'll see that this section here is added onto your equation sheet, and it's only when you have multi-component mixtures, and it's added on for your thermodynamic equations for your A, your H, and your G. And we'll deal with this section, this little chemical potential in second semester. So for now we'll just be using the equations for pure component systems. But that was the last slide to just show you, okay, for Ni components or Nj components, depending on if you use I or J here, then you will have a chemical potential for each of them, and for each of them you'll also need to keep the rest of the components constant while partially differentiating it. And yeah, that was the lecture. And then because you also know Maxwell relations and Legendre transforms, you can even form even more identities or new functions using Maxwell equations. And later on you'll see a nice one where you see dg by dni is equal to your mu and I, and that will be quite a nice, that will be a useful one later on, and we'll see where we use it or how we derive it when we're doing multi-component mixtures. But to take away from lecture 1A, 2A and 2B is all your mathematical background development is helping you to develop manipulations in order for you to solve thermodynamic equations, but for you also to be aware that you can work out path dependent or independent processes, and depending on if it's a state function you could always work out the delta U, and you can also use, you also learned a base function of U which is canonical variables of S and V, and from them you can form other thermodynamic relations which we will definitely use in the later semester and get to know more about what the A, H, G, S, P and V represents.